Thank you for attending. We're giving an update on Blue Earth County Ditch 57. How many here have not heard us talk about CD 57 before? Have not heard it? A couple. I'm just asking to see how much time we should spend on the history or if we should spend more time on the results. So I'd like to spend more time on the results based on the crowd that's here. So I'm Chuck Brandel with INS Group. I was the engineer for the Blue Earth County Ditch 57 project.
I'm Craig Ostenson. I'm the ditch manager for Blue Earth County. I was a ditch manager at the time for this project here. And
I have to give thanks to the LCCMR and the Environmental and Natural Resource Trust Fund. Without the funding we got from them on this project, we wouldn't have been able to do what we did. CD 57 is in Blue Earth County, near the city of Mapleton. It's a 6,000 acre watershed. It was originally constructed in the mid-1910s. We have found remnants of tile in this system that were before 1900. So there's portions of the system that are relatively old. This line is the watershed boundary. It encompasses the entire city of Mapleton. It was originally constructed as an all-tile system, and then an open ditch was constructed in the mid-70s. A couple pipes were added, and then an improvement was proposed in 2007. That's what started the whole process.
What was the improvement for?
The improvement was to, the open ditch had ended here, and then instead of extending the open ditch further, a supplemental metal pipe was put in the 70s. And that pipe connected another section of open ditch that was constructed in the 70s. Both that pipe and the concrete pipe were failing. At the same time, the southern part of the watershed had never seen any improvements, and some very large rain events, I can't remember exactly if they're 4 or 5 inch rain events, occurred, and a few landowners talked to Craig, ended up talking to me, and said we need to do something to fix this. But it was partially undersized portions of the system, partially failing portions of the system, which is part of the history. The goals of the entire project were to replace the deteriorating tile system, increase drainage capacity while still protecting downstream landowners and natural features, improve water quality, reduce peak flows, increase diversified habitat, provide a unique demonstration project, and really develop a win-win solution that can be a process for future projects. Now remember, this project started in 2007. By the time we were moving ahead to an improvement, it was 2009, 2010, which in water quality history maybe is somewhat far back, but general history is not. I misspoke, the original system was 1921. We had, oh, this is your section, Craig.
Yeah. Like the original system was, of course, 1921. Like Chuck mentioned, there were portions that were much older that were incorporated into the system in 1921. This system has a history of downstream, upstream landowner conflict. In fact, our last project here, our improvement project in 2000 that we were going to be talking about is probably the first one that didn't end up in court. So it was a big improvement over the past big projects on this particular system. Again, like Chuck said, there are parts, it was falling apart. In fact, we were actually in the process, had received the petition to actually improve it. I got a call from MnDOT saying, you have a problem, your CMP pipe is rusted out, there's a big hole in our right-of-way, and they said the whole thing's shot. And they said, you have to replace this right away. And I was luckily able to tell them we're in the process. So yeah, it was in bad shape.
So like I already said, we had a failing system, we had large storms, the design was 100 years old. So we looked at options for improvement. Originally, to size an open ditch, you size it for a 1-inch drainage coefficient, and we would have needed an 84-inch pipe and a large open ditch to properly drain the middle of the watershed. And then that battle that Craig talked about between downstream and upstream landowners led to a compromise that said, we'll improve the system, but we'll do it with storage in mind instead of increased capacity. So we looked at storage in the middle of the system and looking at reducing the tile outlet. It was an open ditch area, from a 1-inch drainage coefficient down to a 0.6 drainage coefficient, and then supplementing the rest of the capacity with storage. So we would increase flow on the south end, store water in the middle of the system, and then maintain or reduce flow on the north end. We reviewed with the DNR, we looked at different cost-effective options, we looked for outside funding, and Craig will talk a little bit about this later. We wouldn't have been able to do this with some law changes. Petition was completed with a theme that storage is essential to the project, but that landowners would limit how much they would spend on storage. So it was up to us as the drainage authority, myself, the engineer for the drainage authority, and Craig to find the additional dollars to supplement for the storage that we needed. We applied to Bowser grants, MPCA grants, LCCMR grants, everywhere we could. We got turned down, and eventually we reapplied to the LCCMR, and they funded the project. Through that process, we determined costs. We looked at different options, in-channel storage, wetland restorations, surge ponds, enhanced buffers. We had a team selected for an interview. 3 of those people are in this room. And we got a grant awarded of $485,000. After that, we had to find and get the storage areas approved. We did not force any of that upon landowners. We made a list, kind of what Kurt and Patrick were talking about in the previous discussion. Where are the best spots? So we took the middle portion of the watershed and we ranked 1, 2, 3, and we got 2 and 3, essentially, out of the system. We couldn't get number 1, but we got 2 and 3. The grant process delayed the project by about a year, and we'll go through the timeline.
Minnesota drainage law, what made the project possible is actually a change in the Minnesota statute. Again, this is a public drainage system, so we have to follow 103E. In 2000, a portion of 103 was modified to allow the use of external sources of funding. And of course, wetland preservation, wetland restoration, water quality improvements, and flood control. And this kind of incorporated, I guess the surge pond was kind of incorporated a lot of that. And quite frankly, if that law had not been changed, this project would have been either not existed or been much, much smaller, because we would not have been able to use outside funds. In 2014, it's been modified again, 103, to actually what's now called quality multi-purpose drainage management options. And of course, that was part of another speech earlier in the day for those people who are that. For the timeline, doing this process really slowed things down. You can see, kind of compare the standard project versus what would happen on County Ditch 57. Yeah, 2007, that's when the landowners started talking. This is interesting because in 2007, it's one of the first meetings where I went to, or the information meeting, just to start talking, people brought their lawyers. It kind of tells you what kind of, how contentious drainage is.
I think we had 3 lawyers at the first
I think it was
meeting.
3. I couldn't remember, it was 2 or 3, but yeah.
Kurt Dieter was one of them.
And so it started out kind of contentious from day one. Normally, of course, 2000, you go through the process, you go to the petition develops. Well, we had a lot of landowner meetings, which met with various officials, Chuck, myself. I know Commissioner Brender, who happens to be in the front row here, was at some of those meetings. Big instrumental person, and I can't give him enough credit, is DNR. Leo Getzfried, I don't know what he did. They had meetings. I had talked to one landowner who was just hopping mad one day. The next day after meeting with Leo, all of a sudden, hey, we could do something different. I don't know what Leo said. I wasn't at the meeting, but that seemed to switch things around a bit. Again, it slowed things down because now they said, okay, let's do a project. We want outside funding. It took us a year and a half to get the funding, which slowed things down. So we're already to the point where we would be done with a normal project. We haven't even started in construction. So we had 2009. Finally, we got we got the funding. We started actually construction 2010. 2011, we were probably pretty much finished the spring of 2011. And then we basically, so it delayed the project actually about, like I said, a year and a half. 2012, we actually did a lot. That's when we really started the monitoring, and we started getting results.
2012 is when the project was seeded. So at that
Seeded.
point, you could say construction was done.
Yeah.
But in a normal timeline, that probably would have been fall 2010.
Yeah. It was one other thing that delayed us was weather. We get some bad weather for construction. Just lucky that way.
Yeah, if you remember the winter of, what was it, 2010, 2011. We got a record rainfall in September and then record snowfall over the winter. And we started construction in late October, early November of 2010. So.
Then some monitoring started, which brings us actually to 2015 when we just finished the final report to the LCCMR.
Will be submitted tomorrow.
And then, of course, what's also happening, we'll talk maybe a little about, is future monitoring. We did get some additional money to do some future monitoring. I think we talk about that later.
So project components, what did we do? Here's a map of the watershed again. You'll see this a couple times. The blue dots are pre-construction sampling locations. We went out and took base flow sampling before we started the project. And this was just done by ISG. The funding wasn't in place. We took the samples, sent them in, kept the data. They were sent into a certified lab. After construction, the yellow squares are areas where we sampled flow and water quality, and the blue squares are where we just sampled flow. Like I said before, we had an open ditch that we put native grass buffers on. By the time we got to seeding, there were a few areas that had already put voluntary buffers on it. We incorporated a two-stage ditch, which I'll go into detail, pond, which we call the Klein Pond, a city stormwater pond. The city of Mapleton had a stormwater pond that they were, in my mind, underutilizing, and we modified that, made it larger, got more capacity out of it, and that drains most of the city of Mapleton through it.
Why, I mean, that's the question. Looks like the city of Mapleton is downstream from their trunk pond.
The water flows to the north.
But the stormwater is south of the city of Mapleton.
Most of the city drains west. Yep. And historically, this was a low spot. And the city kind of sits high above that. It was probably a shallow lake or shallow wetland at the time. But most of the city, probably, I can't remember the percentage, maybe 80% drains to the west. So the city goes like this and turns around. So. We had an overdug ditch that was part of the system, and I'll go through some of those components. When we were doing our monitoring, our primary components were flow, which we call Q, which is the volume and speed of water, total suspended solids, which we'll refer to as TSS, phosphorus, and nitrogen. I don't need to go into a lot of detail, but how do we look at rainfall events? This top chart is the amount of rain. We'll call these hour increments. You get a peak amount of rain, and this rising limb, this is a hydrograph. Here's the groundwater, or base flow, and as you get more rain, you get more flow, and eventually you get a peak flow, and then it dampens out. So what we were trying to do as part of this project is to take this peak out, to try to lower that peak and spread out this hydrograph, which we'll show you an example later. So the main components that we monitored, I just back up, were the rate control weir, the Klein pond, and the two-stage ditch. The city pond, we have the outlet data from, but we don't have inlet data. There were 3 pipes coming into the city pond, so we know what's coming out, but we don't know how well the city pond is treating the water. But for the Klein pond, the two-stage ditch, and the rate control weir, we've got sample points either right at those locations or right directly downstream and before them. So a lot of our monitoring data is, here's what's coming in, here's what's going out. Let's compare the difference and see how well it's working. The Klein pond, we took 4 acres. South is to the top, north is to the bottom. The ditch flowed in. There's a 48-inch pipe that comes into the ditch with a weir here that blocks flow to force flow into the pond. There's a 15-inch pipe that comes out of the pond, and then I believe a 60-inch pipe downstream of that. The weir will overtop once the pond fills up. That weir is set below the top of the ditch. This picture was taken in 2013 after what we call a 25-year event, which is 2.5 inches of rain over an hour and a half. But this was the next day. ISG just happened to be doing some marketing photos for some sites in Mankato from an airplane, and I said, go down and take a picture of CD57 because we know we got a bad rain event last night, and let's see how well it's working from the air. So, which has been great to use for marketing and presentation, so valuable data. So we got a 48 coming in, a 15 coming out. The pond holds, when it's full, 26.5 acre feet of water. Here's a picture of the pond during the flood event. There is also an overdug portion of the pond that's permanently wet, that's set up for sediment capture, and I'll talk a little bit more about that detail and some of the results. So another component was the two-stage ditch. We constructed approximately 1,400 feet of a two-stage ditch. And a two-stage ditch is, it's a channel within a channel. So a standard ditch, I think it'll pop up, there we go, is typically has, and this might be raised berm or it might be flat, a 16.5 foot buffer, 2 to 1 side slopes, anywhere from a 4 to, I've seen up to 30 foot bottom on a constructed open ditch. A two-stage ditch has a channel inside, then it has benches. The channel is supposed to be sized to handle the low flow and the base flow. So this controls meandering, shorter flow lengths, faster velocities, less sediment buildup. So it's supposed to, whatever sediment is there, it's supposed to move it, reduce the amount of cleanings, but then it moves the your wetted perimeter away from this point here where we do see a lot of sloughing. So in theory, it's supposed to reduce the amount of sloughing, and I think we've seen that out there. The benches, they provide hydraulic capacity for higher peak flow events. They allow for sedimentation and nutrient uptake, and they can provide habitat area, increased vegetation, greater slope stability. And then we put in native grass buffers, which we've talked about all day to provide stormwater filtering. So how does it look? Let's see if we zoom in. Nope, we don't. These pictures might be hard to see. Here's a picture in the fall of the two-stage ditch. There's a channel and the bench. This picture is after that large rain event that we had in 2013. If you can see the different color, how much sediment is actually building up along those benches. Here's a picture of it full during a flood event. The outlet of the two-stage ditch is controlled at that 0.6 drainage coefficient, where if this was a standard ditch, we'd put in a 1-inch drainage coefficient, but we're utilizing a smaller pipe to store some water in the channel. Here's another picture, if you can see it, of the sediment along the channel.
This is County Ditch 86. Okay, this is County Ditch 86. This is ditch, it's actually what people call the Buford Ditch. This is, you can see it's actually naturally creating a two-stage ditch all by itself. This is also, happened to be the same ditch, Patrick, your speaker at noon, actually highlighted in this area in photographs. It just happens to be the same ditch. This is also a ditch that we also putting in a targeted inventory. So we're actually going to be coming up with a better report and actually different multi-purpose drainage practices for this particular ditch system.
At the end of the system, we put in a rate control weir. It's approximately 5 feet high. And the system was very, very flat, 0.1% grade or flatter. But at the end, we had a little bit of slope. And what we did is you put this weir in, surveyed where the lowest tile was coming in to the system, and we were able to store 5 feet of water back kind of in a triangle wedge. And the top of this weir was set 1 foot below the lowest tile coming in. So what I call it is free storage. And a little bit of what some of the other speakers were talking about, Patrick Belmont and others, where can you find storage? Here's a spot that we found storage. So you can see the weir at low flow. This is Nick McCabe, he's about 6'2". So just to give you an idea of height. Here's the weir at high flow, and another picture of the weir. This is very close to the Cobb River, so we do get our peak flow coming out of the system. It fills up the weir. Then as the river comes up, it kind of equalizes, and sometimes even we do get backflow. We have 6 acre-feet behind it before it overtops. So those are the main components that we looked at. I'll go through how we did monitoring quick and get to the results so we could go over those. We had 2 ways to monitor precipitation. We had a rain gauge, then MSU let us borrow their high-tech weather station, and that allowed us to monitor temperature, wind speed, direction, relative humidity, but also it sent a message when we started to get heavy rain, so we could send somebody out to monitor. MSU did a lot of the groundwork. They did a lot of the field work, collecting samples. A big thanks to them, and they are now continuing on with that through a separate grant. We worked with the civil engineering and the biology departments, and they lent us this piece of equipment, which was a little unfortunate because it did get stolen. But what's that?
We got a sweet new weather station out of it. I was monitoring.
You were doing some monitoring?
Dr. Hoffman and I put that up, actually, the weather station.
It was great to have that data. And you guys went out at 11 o'clock some nights and collected data, trying to collect that peak as close as we can to the peak flow to collect samples. Flow monitoring, we used data loggers to record water every 5 minutes. We had staff gauge for manual readings, and then we had a camera take a picture, a trail cam, to verify, to make sure that the equipment that we were getting is taking a reading that the water's 5 feet high. We have a picture that says it's 5 feet high to validate. Our budget for monitoring was developed in 2008, 2009. By the time we got to the project, I would have loved to have another 100 grand to do a better detailed monitoring, but I think we did a pretty good job with the budget that we had. Uh-oh. Why is it doing that? There we go. The data logger setup, we had the pressure transducers. They were put in a tube tied to the structure, and then we surveyed that every year. We had the cameras set up to take a picture every 5 minutes. Like I said before, 12 flow monitoring stations, 7 water quality monitoring locations. We collected data for 3 years. We began as soon as we could after ice out, and we continued through October. I will say the first year of monitoring was a challenge, just to learn how to do it, how to collect data. Fortunately, it was 2012. There wasn't a lot of flow. There wasn't a lot of rain events. We did get some data out of that, but we learned a lot. We took 1 manual flow measurement every month to check. We took 1 water quality sample per month, and we tried to get 1 base flow sample per month. Our grab samples, we looked at total suspended solids, total dissolved solids, total phosphorus, orthophosphorus, nitrate, and nitrate. Like I said, we looked at temperature, pH, dissolved oxygen, turbidity, T-tube. So before we get into the results, what did this cost? The Klein Pond, at the time it was bid in 2010, was just under $150,000, 26.3 acre feet of storage. We had sediment storage of 3.5 acre feet, which is about 560 dump trucks. The total cost of the water storage was $5,600 per acre foot. The 2-stage ditch, to develop this cost, we took the standard ditch and then took the difference to widen it. And that includes land cost to widen it. That incremental cost for 1,400 feet was $27,000. That would not be what it would cost to construct an open ditch. The $19 per foot is the additional cost. To construct an open ditch of this size, I think our bid was about $55 a foot. So call it $60 a foot versus $80 a foot when you're looking at a 2-stage ditch for an open ditch. Now this is constructing a brand new ditch. Now you could retrofit an existing ditch to a 2-stage ditch a lot cheaper than that. The rate reduction weir costs $12,500. We just bid a couple this year. We're seeing prices in the $15,000 to $20,000 right now for the same type of structure with 6 acre feet of storage. So total project costs with everything that was done, monitoring, design, construction, all the equipment, it was $1.3 million. So if we wouldn't have got funding, would this project have worked under the drainage statute? The answer is no. If we take out the monitoring, say that's not required, it costs $856,000 to do a repair in the area we were doing the improvement. The ditch statute allows us to take the difference between an improvement cost and a repair cost, and that's how much benefit you have. And I'm not going to go too much into that because that's viewers' presentation, but essentially we needed to find $291,000 of benefit to make this project move forward the way it was. The viewers, when they did their redetermination of benefits, they had $241,000. So to construct it the way we did without outside funding wouldn't have worked. We would have been short by $51,000, and with contingencies, we probably would have had to cut the 2-stage ditch, the rate control weir, and the city pond to make it work. So with the trust fund, we got $485,000, which paid for the monitoring, some of the design, both ponds, native grass buffers, the 2-stage ditch, and the structures that went along with those. When you subtract that out, you get $826,000. Separable maintenance was $856,000. Well, we get negative $30,000 or zero, which is less than, that means that the $240,000 benefits is higher than that which means it meets the drainage statute. So without outside funding, this project doesn't happen the way it happened.
What was the source of the funding for 485?
It was Environmental Natural Resource Trust Fund through the LCCMR.
That's the legacy?
Legacy money, yep. Or no. Lottery money, yes, yep, sorry.
Ken, could you say anything about why previously they did not allow outside funding, thinking behind that?
Way back when, people would say, okay, the project's not going to work, I'm going to kick in my own funds to make the project work. So that's kind of an historical thing. And they, of course, that was before they even thought of any type of wetland restoration. It was just for drainage. So it's kind of an artifact of issues previously, maybe even 100 years ago, 50 years ago, when they first established drainage law. And by today's standards, when you look at a project like this, yeah, it doesn't make any sense by today's standards, but it made sense back, 60, 100 years ago.
I want to get to the results. Here's some of the wildlife we captured on the cameras. Here's some construction pictures. We had a 54-inch RCP that went in as the outlet of the two-stage ditch. We had some pretty wet conditions. Here, the two-stage ditch was constructed during the winter. And we had some flooding in the Klein Pond that had made us stop construction for a while. There's construction of the city pond, completed Klein Pond right before we seeded and mulched it, and the rate control reel right after it was constructed. So, calculating results. How did we do it? We had the surveyed ditch geometry. We determined stage from the data logging and the pictures that we had every 5 minutes. Then we took that information, used Manning's equation, engineering term, and developed a hydraulic and hydrologic model in HydroCAD to approximate flow. We looked at the amount of rainfall and runoff depth throughout the watershed, and then we calibrated that throughout the system. So we had these 12 points where we had flow, we had the rainfall data, and we calibrated it. Now, we were limited to 12 points in the system, so our data does have limitations. For nutrient calculation, we took the water quality samples that they were taken at 11 o'clock at night right after the heavy rainstorm. We got concentrations from those samples, and then we used those with our flow calculations to determine loading. And then we compared the loading upstream and downstream of the BMPs to look at the differences in reductions. So our water quality outcomes, I'll go through. For most of our water quality data, we use 19 rain events, which is about 45% of the rain event during the growing season, of the rain in the growing season. So these were all the rain events. You can see 2012, 2013, and 2014. Just note that this is all really one big, long storm event. And here's how much, like I just said, we got 44% of the rainfall during the growing season. So this is the blue line is the percent for each growing season. Green is how much rainfall depth we sampled. Blue is the total rainfall that we got during that growing season. So when we're all of our results, here's a summary of how we reduced peak flow. The Klein Pond, on average, what goes in, what goes out, 28% reduction. Very good results. That's slowing down the flow. The rate control weir was 6%. The two-stage ditch is not shown on here because there's an additional 500 acres that come in between our sample points. So we always had an increase in flow because we had that big chunk of watershed that came in. But the two-stage ditch still reduced TSS, phosphorus, and nitrogen. This is our average reductions for the 3 years. The Klein Pond, 25% on TSS, 19% on phosphorus, 23% on nitrogen. The rate control weir, 6% on TSS and phosphorus, no increase, or there was an increase in nitrogen. And the two-stage ditch, we saw 5% decrease in TSS, 10% decrease in phosphorus, and 4% nitrogen. Now, the two-stage ditch is also directly downstream from the pond, so that might have dampened the results for the two-stage ditch. But it's a positive that even though we increased the watershed by about 25%, we still got reductions in TSS, phosphorus, and nitrogen. So we did all this with a model, samples. We know everything was not perfect. So we went out and surveyed the pond to see how much material was actually in there. Based on our 44% of the rainfall that we caught, we estimated that there'd be 300 cubic yards of sediment in the Klein Pond based on those events. We had surveyed it right when it was completed construction. You saw the picture. That's the blue line. The red line is what we surveyed last fall. There's 725 cubic yards of sediment built up in the Klein Pond. So whether our results are skewed or not, there's physically that many yards of sediment that have built up there. That's equivalent to 70 dump truck loads of material. So just that shows that we're doing something positive to the system. Here's a breakdown. I'd previously shown you the average BMP reductions. Here's the reductions for each year. 2012, we did not have a lot of flow. The pond worked very well. For some reason, the two-stage ditch worked very well for phosphorus. The 2013, I think we had maybe not the perfect year for farming, but for treating water, we had a lot of 1-inch rain events. We had some larger events, but really the pond was working right at what it was designed for, the events that we got. And you can see we've got a 41% reduction in peak flow, 34% reduction in TSS, 21 phosphorus, 26 nitrogen. 2014, we got a little bit crazier rain events, and we got one event that really overwhelmed the system. And in doing so, I think that reduced our results from the fact that the system was inundated for a longer period of time. One thing that nobody has really seen this data before, if you don't believe the 19 rain events that we sampled, we took base flow samples. If I go back to the map, we took base flow samples here, but we also had a sample point after construction here. We took base flow samples here and had a sample point right next to that. We also did the same thing here. So this area is treated by part of the two-stage ditch and the pond. This area is treated by everything, and this area only receives treatment from the city pond. So we've got 3 base flow samples to compare to. And when we look at the outlet, here are 4 of the pre-construction samples versus the post-construction samples. This is just the concentrations in the water sent to a lab. Look at the differences of running through BMPs on the base flow. TSS is way down, 33% for these samples. So, now we were limited to this many samples, but it really paints a picture. When you go into site 2, same thing. Not as drastic, but you still see a 9% reduction in TSS, 10% reduction in phosphorus. Now nitrogen was very close. We did increase the tile downstream. We did have a better working tile system, and that may account for the the difference in nitrogen, or there's no change in nitrogen. But I think this is very good data, just that our base flow numbers were down, that we were catching sediment during base flow and storm events. And then when you go to Site 7, which didn't have as much BMP interaction, they're about the same. So just the base flow samples were very important just to start showing a picture. And here's a summary of those examples. So the dark blue is pre-construction, the light blue is post-construction. And you can see for Site 1, 4, and 7 what the changes were averaged out over the 3 years. And you really see right here that we're capturing sediment. And when we survey the pond and we see 725 yards, that backs up some of our data. There's always a question of how much of the city contributed to this watershed. And we only had one sample point coming out of the city, and that was after the city flow went through the city pond. And the city pond's about 26 acre feet. So it's a dampened flow. So it's hard to compare what was coming into that pond versus what was coming out. So at this point, we just took the data of what was coming out of that pond. And when we look at what is the percentage of runoff coming off the city at that location based on the entire watershed, and it was on average about 5.1%. But I have to kind of asterisk that's after going through a pond with a restriction. So the city pond and the improvement to the city pond did dampen the flow, because I think the city is about 15% of the watershed. So the pond was working there.
So what does that actually tell you? If there's 15% of the land is in the city, you're saying only 6% of it's coming from impervious surfaces, where farmland has more water contribution than impervious surfaces?
This is just telling us that the pond is reducing the flow, so it's only 5% of the flow coming into the system, the city pond. What needs to happen is there needs to be more data in the city to see what is coming into that pond to really do a good comparison of city versus ag runoff. And then I think that's something that could be looked at.
Well, when you're calculating these out, there must be some kind of a formula used for impervious surfaces versus ag land. What percentage of the water is coming from the city, do you think?
I don't have data on it, so I'd have to do a calculation on it. But we had estimated, I think it was 15 to 20% of the flow was coming from the city. So the city pond is actually reducing that significantly. Well, we've got, the city pond is designed, and I didn't go into detail on it. There's 3 large pipes, and I can't remember the sizes, if they were 2 48s and a 24-inch pipe that come into the city pond, and we restricted the outlet to an 18. So we're drastically reducing the amount of flow that comes into that pond. We dug a big hole, and it fills up. No. No. This is just percentage of runoff during the rain events that we captured. And the city loading compared to the watershed loading, those are just the percentages that we got out of the pond. Now, the next step we need to do is survey the city pond to see how much sediment we caught. I just wanted to put this on the board to show kind of a picture of 2013 versus 2014. This green line is the MPCA standard for TSS concentrations in a watershed of CD57 size. You can see 2013 we're doing okay, but then we get that real bad event, and just to show what that did to the system. One of Pat Duncanson's grain bins ended up in the pond. We had a couple blowouts on the system. So you just can't size for that kind of rain event. This is a somewhat complicated chart, but before I showed you that hydrograph, so here's some of a summary of some data. This is what's coming in, this is what's going out, and we're storing the runoff here. And it has a summary of a lot of different data. This shows our sampled precipitation versus the total precipitation during the year. This shows our highest upstream flow on the south side of the system, middle of the system, and our highest flow at the outlet of the system. You can see it's 480 CFS. Here's our largest rain events for each year. Here's our yearly volume of water that we calculated through the system. You can see the differences between 2012, 2013, and 2014. And then here's our storage volumes from each of the BMPs that we calculated, or the city pond, Klein Pond. There were a lot of challenges during the project. Cost effectiveness and drainage law. Without the funding, we wouldn't have made that work. Monitoring is a challenge, just from the standpoint of we have a system that might flow both ways, and we're monitoring a stage and assuming that it's flowing downstream. So there could have been some events that could have been skewed because the water was backing up. Design and installation, weather was really the problem there. The overdug ditch, which I didn't talk a lot about, did not work well here. We overdug a ditch by about 3 feet, and just the soils were non-cohesive, and we got a lot of sloughing from that. Maintenance, you always have to maintain systems. Landowner participation, that really, it was a challenge to start out with, but once we got everybody on board, we had very good landowner involvement. Agencies sometimes slowed us down, sometimes got in the way, and time. So how does this affect other projects? This is a map of projects that I'm involved with that will be incorporating some sort of BMP. And we've learned a lot from CD 57. So we're using that to pass it on to other projects, so it can really do some good in the watershed. So, what's next for CD 57? The report's finalized. It's done. We just have to hit print and send. The Department of Ag and MSU got some money to continue monitoring, and that's currently happening right now. There's potential for other practices to be implemented in the watershed. We're developing new water quality ideas. We've learned some things that worked and some things that didn't work, and we're applying those to future projects. Future cooperation with agencies and landowners. We're showing something that works. It works. The production was increased in the watershed. By my observation, water quality was increased in the watershed. And with all of the data and pictures, we can show landowners that this works. I've had landowners that have told me I'm crazy to design a pond and it's going to flood all the fields around them. And I show them the picture of the pond during that 25-year event, and they say, okay, you might know what you're doing, but it can work. We handed out a little fun facts sheet just so you've got an idea of some of the things that happened during this event and during monitoring. The largest recorded flow based on our updated results is 480 CFS. Our largest reduction, May 31st, 2014, the pond reduced flow by 69%. Sediment TSS 50% on May 18th, 2013. Our highest water level recorded was 12.3 feet in the Klein Pond in June of 2014, that event that inundated the watershed. The largest volume of water through the system, 290 Olympic-sized swimming pools. There's a lot more fun facts we could come up with the data. Our longest drought was approximately a month in 2012. It's the first public system with a two-stage ditch. I talked about the 25 bushel grain, 250 bushel grain bin that was caught in the pond. That's our largest particle of sediment. We did not include that in our results. That would have skewed the results, I think, because that was caught by wind and not by flow. Yes, yep. It did not go downstream. We've 6 species of birds caught on camera, 5 species of mammals caught on camera in the BMPs. There were a lot of acknowledgments. I think we covered most of them. Blue Earth County, County Board and staff, Craig Austenson, Kip Brunder, Will Purvis, the rest of the county board, everybody at ISG that worked on the project. We had a whole team of people. I get my name on the project, but really I couldn't have done it without them. Department of Natural Resources, Leo Getzfried was a huge help. Department of Ag, Mark Dietrich. We had some involvement with Bowser and Al Keen and his staff. The landowners, Pat and Chris Duncanson, Dick Nino, Dave Keller, along with the rest. There's more than just that. Jared Bach from the SWCD offered support. MSU, Steve Juchel, Bryce Hoppy, and all of the students that helped out on the project. And then the city of Mapleton, Patty Woodruff's here. They donated their land for the city pond. There's a lot of data. This report will be put on our website. It'll also be put on a link to Blue Earth County's website, and it'll be on the LCCMR. There's going to be 2 reports on the project. One we call the final report, which has everything that we said we would do. And then we have a supplemental report, which is the water quality report. For those that want to see, we have all the equations we used for calculating all the data. We take one storm and we break it down and say, this is how we came up with the data. So if anybody questions it and wants to see how we did it, it's all there for those to see. So, yes.
I'd like to ask Mr. Duncan and the other farmers here that after this is done, I guess the object for an individual landowner is to be able to see that their water can flow into the system in an adequate way. Is that objective met?
Are there any other landowners? I don't think so. I think I'm the only one. So I was one of the original petitioners, and that was our goal, is to increase the drainage to our farmland. Actually, Patty from the city is here at Mapleton as well, so I guess you're representing landowners. Before the improvement, and actually my dad was involved in the 1970 improvement. My son is sitting here, and I sure hope that he doesn't have to go through an improvement project in another 20 or 30 years. I hope we're done. But we went from after the 1970 improvement, the farm in front of our house had about a 0.3, 0.35, Chuck, coefficient. 0.3, yeah. And so we were looking for an improvement from that. I wanted the 1-inch coefficient. I would have called that the Cadillac system. We didn't get a Cadillac, we got a Chevy system. But our Chevy system, even though the pipe is at a 0.6, I think our effective coefficient for most rains, most storms, is going to be much greater than a 0.6. So I think our effective drainage coefficient is more like a 0.75. Yes, we got an improvement in drainage. Is it the absolute best Cadillac system? No. The other thing was the political reality is the landowners in the system are very, like a lot of systems, they're very articulate, they're very astute, and many of the downstream landowners were recognized that they could make the petitioners' lives miserable, and they could also greatly escalate the cost of the system. Quite early on, we recognized the political reality is that if we decided to push ahead and go for a 1-inch drainage coefficient system, we may never get it built. And the other thing is it would have been incredibly expensive from a legal standpoint. So we compromised. That C word is a nasty word sometimes. We compromised. We don't have exactly the ideal system that I wanted when we started. We've got a system that I think my son can probably live with.
I'm going to attest for a landowner that was very adamantly against this. And essentially, he got a clause in the petition that was, we don't trust the engineer clause. And he's up in this area. There was a clause in the petition that said if this storage didn't work and we got too much water on us, we can upsize our culverts to let that water out. That landowner, I'm currently working on an improvement in another watershed with, because he's very satisfied with the result, because these guys got an improvement and he didn't get flooded. So. Oh, shoot. I should know this. It's not. I can find that out. I need to find that out. I can't remember exactly what seed mix it was, because it was 2 MnDOT seed mixes ago. I
And
just
one
can't-
of the things that required, the LCCMR required, that it had to be all native species.
Yes, predominantly wetland native grasses with some native flowers, but mostly native grasses. And we did a 3-year maintenance contract. So the contractor seeded it. We checked on it. He had to mow it a certain number of times per year. There was a little bit of spraying, not a whole lot. But there is some maintenance that we need to do now on it. So, I think it is. And that was the goal, was that we would do all of the buffers in the native seeding, the ponds, the 2-stage ditch, everything in native seeding.
How do you see integrating this with one watershed, one plan, and the RAPS? How do you think that can help your process within the drainage district? And how would you go about that? Normally these things wait until the petition comes around, but if you get ahead of it.
Well, part of it, if we look at, like we talked about this morning, looking at doing multi-purpose drainage management plans on some systems, getting plans in place before the petitions come forward, identifying, like Kurt and Patrick said, identifying the best place for storage. Then when a project comes up, the petitioner's got to get on board that they need to do that. I guess that would be one way to incorporate that in.
Chuck, what is the black square to the northeast of Maple on your map?
Oh, right here? Yeah. Those are the sewer treatment ponds for the city of Mapleton. And we did not have, we had a flow monitoring point at that spot, but we did not monitor water quality. That was not part of this project, so we didn't look at that.
Hopefully that's not going into the system.
It's twice a year, it's outletted into the system. As most sewer treatment ponds are done, they're emptied out twice a year.
Did the original system have open ditch and tile and more open ditch, or how come you said put that back in?
The original system was all tile, and then in the 70s, this portion was open ditch, and then it stopped here for, and Pat knows the history better than I do, for some political reasons. A pipe was put in this stretch, and then an open ditch was constructed, and then the rest was pipe. So the whole upper end of the watershed was restricted by this pipe. Yes. And we did compromise again, and that 54-inch pipe is across that property now. So
I'm still back on that one slide that says 6% of the water came from the city. What does that slide tell us? I guess I'm confused at what that's measuring there.
it just says that at this point, 6% of the water running through the watershed is city drainage.
But how much percentage of the city of Mapleton is that goes this way then?
I think it's about 80 to 85%. Yeah, so that doesn't include the wastewater treatment ponds, and it doesn't include this part of the city. So more detailed study would have to be done to see what the total effect of the city is.
In your judgment, that seems realistic, that only 6% of the water is coming from that chunk of the watershed?
Because we have a large storage pond, it does, but,
Well, the 26 and a half feet's really only a half inch of water, isn't it, on the whole watershed?
but the storm sewer system in the city also limits how much water can get there too. So the point of that is that it needs more study. We have one data point for the outlet of the city. And
You think it's somewhere close to 6% then?
coming out of that pond, I think our flow data is very good coming out of that pond.
You've got your backs.
What's the future of the sediment?
The sediment in the pond, we anticipated that we would clean like an open ditch. So we go back to the,
As these things are more successful, we're gonna have more sediment.
we're gonna have to find homes for putting the sediment back on the landscape. So this portion here and this portion here are wet portions of the pond. We anticipate cleaning this like an open ditch, and hopefully we can get participation from these landowners to put it back on the field.
There may not be a lot of experience with redistributing sediment.
Well, ditches are cleaned every year, and that sediment is taken back up onto the landscape. So it's the same, we're trying to follow the same procedure. We tried to design it to be on the same maintenance schedule, so that way when the ditch is cleaned, the pond can be cleaned. Hopefully, see how that works out. It seems like it's working out well. We got to get back. You got to give a closing, Kip. So, thank you.